All right, folks, there are about three main examples that we need to look at in this section. So let's start off with our first one. Find the length of the curve y equals x squared from x equals 0 to x equals 2. So first, although it's not strictly necessary, we might want to consider drawing something like this. Let's see, here's 1, here's 2, 1, 2, 3. I'm running out of room already. Up a little bit higher here. Come on now. Up a little bit higher here. And there's 4. So 1, 1, 2, 4. Here's x equals 0. Here's x equals 2. And the parabola looks something like this. And that's the length that we want to find. So this is y equals x squared. So the arc length formula is pretty straightforward. A lot of this is plug and chug. The integral from a to b of the square root of 1 plus f prime of x squared dx. For us here, a is equal to 0, b is equal to 2. We can do this with respect to x, no big deal. And if y is equal to f of x is equal to x squared, then y prime equal to f prime of x is equal to 2x, and that makes f prime of x quantity squared equal to 2x squared, which is 4x. Quantity 2x squared becomes 4x squared, and L is the integral from 0 to 2 of the square root of 1 plus 4x squared dx. So one of the reasons that we do arc length so late in this particular book is because many of the integrals that you end up with involve trig substitution. There's just kind of no way around that. So let's get started on that integral. So L equal to the integral from 0 to 2 of the square root of 1 plus 4x squared dx. I suppose if we're going to be overly formal about this, let's rewrite that as 0 to 2, the integral of 1 squared plus 2x squared dx. And so according to this format, it is a sum of squares where a is 1, w is 2x, and according to a squared plus w squared, we need to let w equal a tangent theta. So in this case, we're going to let 2x equal 1 tangent theta, so that 2 dx is equal to secant squared theta d theta. And we can begin our substitution. This is from x equals 0 to x equals 2 of the square root of 1 plus 2x is going to be tangent theta squared, and then d theta is going to be secant squared theta, or sorry, dx is secant squared theta d theta over 2 as we solve that for dx. And cleaning this up, we get 1/2 the integral of secant cubed x equals 0 to x equals 2. This is secant theta times secant squared theta d theta. Now, we can either go through the rigmarole of integrating that right now, or we can have that secant cubed integral memorized. X equals 0, x equals 3, secant cubed theta d theta. I think for this example, we'll just keep rolling. We were told to remember that as the average of the derivative of secant, which is secant theta tangent theta, and its antiderivative, which is the natural log of the absolute value of secant theta plus tangent theta. And then from x equals 0 to x equals, oops, I don't know why I got a 3 there, x equals 2. Okay, so what do we have? We have 1/4. Let's undo our substitution. Our substitution was tangent of theta is equal to 2x. So we'll put theta in the corner here. Let's rewrite that as 2x over 1 so that we actually have a ratio. And so this is a ratio of opposite to adjacent. And that makes the missing hypotenuse the square root of 1 plus 4x squared. So when we use that information here, we have the secant of theta, which is the hypotenuse over adjacent, which is the square root of 1 plus 4x squared, times the tangent, which is 2x, plus the natural log of the absolute value of the secant, which is 1 plus 4x squared under the radical, plus the tangent, which is 2x, all evaluated from x equals 0 to x equals 2. And this becomes 1/4, and when we plug in 2, we get the square root of 17 times 4 plus the natural log of the square root of 17 plus 4. And when we plug in 0, we get 0. Not just because that number is 0, but if you actually physically take the 0 and plug it in here, you'll get the square root of 1 times 0, which is 0, and then the natural log of 1 plus 0, which is also 0. And so that's our answer, and this is the square root of 17 plus the natural log of the square root of 17 plus 4 all over 4, or I can write that as the 4th root. Any way you want to write that. But there's our answer. That's our arc length. It's not pretty. Let's get a decimal approximation for that, if we can. Let's see. Square root of 17 is about 4.123 plus 4 is about 8.123. We'll take the 4th root of that. 4th root is about 1.688, and then we'll take that natural log, and it's about plus 0.52, rounded up 524. And the length of that arc is approximately 4.647 units of length, whatever that is, miles, centimeters, astronomical units, light years, parsecs, whatever you're into, man. I'm into light years and parsecs, but that's just me. Anyway, that's a typical example. There are problems that have easier integrals to deal with, and we're going to do those in our, I should say, quote unquote, easier integrals to deal with. We're going to do those in the next couple of examples.